Let's try some practice from worksheet 5.6, writing equations in standard form. Remember, this is our standard form template. A, B, and C have to be integers. This has to be positive. A has to be positive, and then no fractions or decimals for A, B, or C. Which also means integers, specifically A being positive though. Alrighty, so why doesn't number 1 look like it's in standard form? It's because while x and y are on the left, that is good. There's a plain old number or a constant on the left, so let's undo that. So we get x minus y equals 9. Same thing with number 2, I would say, right? And same thing with number 3. Notice number 3 doesn't have a y. That is okay. Your answer will not have a y in it. Number 4 is kind of silly. It's actually in really good shape. Your x's and y's are on the left, but technically we want our x term, our independent variable, first. So I just rearranged, addition is commutative, so I can rearrange the order that I add things. Just did that. Let's try number 10. So there's an x on the right, so I need to undo that because I want the x's on the left. So when I undo it from the right, I have to subtract 5x also on the left. So I get negative 5x plus y, because the y is positive, equals negative 1/2. So remember, A, B, and C, my coefficients here, there, and there, have to be integers. And the A one right here has to be positive. So I have 2 issues. A here is negative. Any other value, the coefficient of y and this number can be negative, but this one is negative, and that's a problem. And then my other problem is that this is a fraction. So to undo that fraction, to undo dividing by 2, I'm going to multiply by 2. And to undo this negative, I'm going to multiply the negative. In fact, I'm going to have to multiply everything by a negative as well, because a negative times a negative is a positive. So here I get 10x. Awesome. It's an integer, and it's the A coefficient, and it has to be positive, and now it's positive. Here I get a negative 2y, so minus 2y. And then here, negative 2 times negative 1/2 is positive 1. And it's not a fraction anymore. That's what I was going after. Got rid of that fraction as well. That's awesome. Let's try another one. Number 12. There's an x term on the right, so we have to undo that by adding 2/3 x, because a negative 2/3 x and a positive 2/3 x are 0. It's gone. But what I do on the left, or excuse me, what I do on the right, in this case I have to do on the left. So I get 2/3 x plus y equals negative 1. So A is positive, but I can't have any coefficients that are fractions or decimals, and this is a fraction. So I need to undo dividing by 3. And I undo that by multiplying by 3. So I take 3 times 2, which is 6. And then I have to take 6 divided by 3, which is 2. So I get 2x plus 3y equals negative 3. Distributing that 3 to every term here, including across the equal sign. Write the equation, or write the standard form of the equation of the line that passes through the given point and has the given slope. So we're using point slope form here to start with. So we would get y minus 5 equals negative 3 times x minus 2. Distribute first. Careful here. I like to add the opposite. Oh, I'll do it in a red. I like to add the opposite. So we get negative 3x. I'm going to drop the plus sign down, and we have a negative 3 times a negative 2. That's a positive 6. Last step, undo subtracting 5. So we are now getting it in slope-intercept form, folks. But it's easy to move things from slope-intercept form into standard form. Why is this not in standard form? It's because the x term is on the right. So we need to undo that by adding 3x. So we get 3x plus y equals 11. Beautiful. Shoot, I think I missed one. It's unfortunate. Oh yeah, and we need the information with it. I think it's right here. Let me see if I can take a picture of it or just grab it. Bump, bump, bump. There we are. So, you're running for class president. Good luck. You have $30 to spend on publicity. It costs $2 to make a campaign button and $1 to make a poster. Write an equation that represents the different numbers of buttons x. So the buttons on the number of x's are the x represents the number of buttons, and y represents the number of posters we could make. And we're supposed to write an equation. And I have $30 to spend. So if I'm going to buy buttons, buttons cost $2. So it's going to cost me $2 times every button, every X that I buy. So if I bought 10 buttons, it'd be 10 times 2, that's 20. And this expression, 2x or 2 times x, does just that. I take 2 times the number of buttons I buy, and that seems like that's what it should cost me. It is. That's what the story is telling me. And it cost me $1 to make a poster. And y is the number of posters. So if I order 8 posters, it'll cost me $8. So I take $1 times every single poster that I order. So 2x plus 1y equals 30. That's, I think, a good equation, a great equation to show what we can afford. Sketch the line that represents the possible combinations of buttons and posters in exercise 25. So in the problem that we just did, complete the table and label the points from the table on the graph. So what if we order 0 buttons? How many posters could we do? We could do 30. Remember, it's $2 for every button and $1 for every poster. If I order 5 buttons, that's going to be 2 times $5 plus 1 times the number of posters I order. That brings me to 30. So like here in my mind, I'm thinking, well, that's $10. So that leaves me with $20. So that means I could buy 20 posters. Let's try buying 8 buttons. So if I'm trying to get as much stuff as I can, if I buy 8 buttons, how could I max out my $30 with posters? 2 times 8 is 16. That means I have $14 left over. So I could buy, because every poster is $14, I could buy 14 posters. And let's try 10 buttons. So if I buy 10 buttons, that's $20. I'm only going to have $10 left, so I could buy 10 posters. And last but not least, if I buy 15 buttons, that takes me to $30, so I don't have any posters that I can buy. So let's see, the x-axis is buttons. Y-axis is posters. I think I'm going to need to scale this to get up to 30. So if I make every square worth 2, it should do it, I think. And then notice I'm skipping 2 squares at a time. Oh my goodness, I might not. Oh, I think I will. There's 28. So then there's 30. That'd be 32. And then down here, if I look at my x-axis, I notice that it only has to go up to 15. However, I'm just going to keep the scaling the same. You don't have to do that. In fact, part of me really wants to just string it out, make each box worth 1 button. But posters and buttons, I guess this is our campaign. They use a word for that. Publicity. That's a good word. Campaign, publicity, budget. And it's not the budget, it's really just tools we're using for campaigning. But let's just start going with this. So 0 buttons gives me 30. posters. Boom. 5 buttons, 20 posters. So 5 would be right in the middle of this square. 20. Right about there. 8 and 14. There. 10 and 10. 10 and 10. 15 and 0. 15 would be right there. Hate to brag, but, well, before I brag, let's move that. But I'll tell you what, I think that makes a straight line. This is a linear function, folks. And those 5 red dots I made, I believe, make a super straight line. Yeah. So what this line represents, folks, now technically it should just be integers because you can't buy a half a button or a half a poster. So all of the integer combinations going down this line work. Our table is 5 combinations of things that we can do, but there's many, many more ways that we can spend $30 on different combinations of buttons and posters.